So now we're going to get on to instructions for downloading the Mutable Instruments code from GitHub. So the first thing you need to do is to navigate to Git. There's the web address, and there's various options here. So if we go down to standalone installer 64-bit Git for Windows setup, if we click on there, and that downloads, and now we need to install that. So now we need to run GitHub. So if we navigate down to the start and type git, and if we go to git command, type cd/. So now you need to create a folder where you're going to put all the code. So I've created one on the desktop, and it's called GitHub test, just for purposes of teaching you how to do this. So now what we need to do is copy that path, and then navigate to the git command window which you just started. If you type cd and paste, enter, now we're in the correct directory, and now we can issue the first command to start cloning the git. So the first command to execute is git clone https :// gi.github.com/pishnets/mutable -dev-environment.git, and press enter. So the process is started. So going back to the directory where we started, GitHub test, you can see that last command has actually created a mutable dev environment. So now if we copy this path, go back to our git command window, we need to change directory to the path with the development. So if I do cd / to come right to the end, or back to the root. So we're back at the root. If I type cd, copy that path, and then enter. So now we're into that directory there. So the next command we need to execute is this one: git clone https :// pishnets/eurorack.git, and press enter. So that's completed. One more command to do. So the final command is git submodule init and git submodule update, and press enter, and that completes this part of the video. Right, let's talk about programming. So I'm in the Mutable Instruments documentation. I think we've seen this web page previously. There's the module. So let's go to firmware hacking. So if we scroll down in here, description of the process. But there's an interesting statement there. When we actually upload the firmware with that command make fstages make file upload, it says know that this will destroy the factory calibration data. So that's assuming that we're actually going to do this on a bought module that's come from the factory. We're not actually going to do that. But if we move down a bit further, it describes this. So there is a factory calibration routine, and basically it does the scaling of the ADC and DAC for each channel. So there's 6 channels, so we've got zeros at the top there and 5s at the bottom. So 0 to 5, that's 0, 1, 2, 3, 4, 5, that's 6 channels. We need to, for testing purposes, to make it work, we need to put this data into the microcontroller. So what these lines of code do is add some values, those values there at the end, into memory locations, and when the microcontroller does its work, it scales the ADC and DAC for each channel appropriately to make the output work. A directory on your computer called Mutable Instruments Firmware, and a Mutable Development Environment, Eurorack modules, and of course we're building stages. So in this particular directory there is a file called settings, and it's the CC file. So opening the settings CC file, we see this. It's a bunch of text, and if we scroll down you can actually see the code in there. So what I've done is I've added those lines of code that I've just talked about for each channel. So you can see the channel 00, that's 1, 2, 3, 4, 5, 6. So they're for the DAC scale and offset, and below it we've got the channels again 0 to 5, and these are for the ADC offset and scale. So basically I've added those in to that code. So where have I put it? After that fill statement, right at the top, and before the state color blind equals 0. So in essence, what that will do, when I initially flash the microcontroller, upload the program, it will add these values into these memory locations, and it should make the module work somewhere near correct. It won't be perfect, but it'll be good enough for us to check that the module is actually working. So why do we have to calibrate the module? Well, here's an example. I'm looking at my schematic, and I'm looking at the CV input 1 there, and as you can see it's coming into an op amp, and the output goes to the ADC. Well, as we know, there are tolerances around all those components. You see the 100k resistor R17, R11 30k, R12 20k. Well, those will have slight variations which means that the value that the ADC sees might not be what we expect. So there's our first source of variation. Our second source of variation is the DAC output comes through an op amp. Obviously that 20k resistor might not be exactly 20k. That 130k resistor might not be 130k, and so on and so forth. And that eventually finds its way out to the output jack. So there's another source of variation. Right, we need to create the software environment to allow us to do the programming. So Mutable Instruments recommend using VirtualBox. So if you can see there at the top, this is in my downloads file, so these are ready to install. I've got Oracle VM VirtualBox extension pack, that needs to be installed, and VirtualBox 7.0.14. Let's install those and see. So I've installed VirtualBox. There's an icon to run it on my desktop. Let's have a look. And then we're greeted with this screen. So at the moment, my understanding is this is a virtual machine, which in essence is conceptually a virtual computer inside the operating system. I'm running a Microsoft operating system, I think it's Windows 10. This creates an environment which Mutable Instruments use to do their programming work, and we need to create that inside here. So at the moment my understanding is that there is no virtual machine running. Let's go and make that happen now. So the first stage is to navigate to our Mutable Instruments firmware, Mutable Development Environment. Now, if you see in here, there's something called a vagrant file down there. And the reason for that being there will become apparent in a moment. So we now need to open a shell window. So if you come down to the Windows icon, click on there and then type in shell, you'll be greeted with that. So what we need to do now is open a shell window. And basically we're greeted with one of those. So what we need to do now is navigate to the folder that I showed you previously. So let's try to do that. So if I click on that and copy, and if I type CD there, so let's change directory, space, and paste that path in. So now we're in that directory, as you can see there. So that's the first. So now we're in that directory. If we go back to this, there's a vagrant file there. So if I type the command vagrant up here now, let's see what happens. It's starting the virtual machine. Now, this takes for 5 to 10 minutes to do. There's quite a lot of things going on in the background. So I'm going to pause here and wait until I'll come back when it's finished. So here the process is finished, and it's come back to the prompt. So next command is vagrant up, press enter. So we're now actually into the virtual machine. Um, let's have a look at the programming device. So here is the programming device. This is what Mutable Instruments recommend. This is a STM32 Discovery board, Discovery 1. On the side there you can see is a header called SWD, that's Serial Wire Debug, and there's actually 4 wires coming out of there. They will be the 4 wires which we connect to our microcontroller on our new board. This actually piece of kit does a number of things. We're going to use it as a programmer, but it has other capabilities. To use it as a programmer only, we need to remove those 2 jumpers there, and we connect this board via that USB cable to the computer. So here we are back in the virtual box, and as you can see, that code we ran earlier now means that there is a virtual machine running. So what do we need to do now? Well, the ST Discovery board, which we were going to use as a programmer, you need to ensure you've got the appropriate drivers, and you can get those from STM on their website. That's the first thing. But clearly the virtual machine needs access to the USB connectivity on your laptop. So we're now going to check. I've actually plugged the Discovery programmer board into my laptop, and we're going to check whether the virtual machine can actually see that USB. So if we come up here to, where's my mouse, settings, there, zoom out a bit, right, we can see down here is USB. Let's click on there. So we've got a whole bunch of filters there, but I don't see our device there. So what we need to do, I think, is come over here, add new USB filter, press that, and there it is, look, ST Microelectronics STM32 ST Link. So if we press that, it's now added it to there. That's very important. I had a problem with this the first time I used it, and that wasn't automatically selected, and of course the virtual machine couldn't see the USB, and I couldn't program anything. So if we press OK, now we should be ready for programming. So there's a few more things to do before we actually flash the microcontroller. I'm back in here, open source Mutable Instruments documentation. This is where we were before. And scrolling down there, the first thing we need to do is create a bootloader. So in the virtual machine that we've got running now in the background, we'd type that code in, make F stages /bootloader /makefile hex. We'd do that, and that's going to store that hex file in the directory that I showed you earlier. And then we need to build the code, so we put that command in and run that. And then all we need to do is upload the firmware with that command there. And I managed to get success, so I hope you do too.